The apparent depth of a needle lying in the bottom of the tank, which is filled with a water of refractive index 1.33 to a height of 12.5 centimeters, is measured by a microscope to be 9.4 centimeters. If the water is replaced by a liquid of refractive index 1.63 up to the same height, what distance would the microscope have to be moved to focus on the needle again? The options given are 1.73 centimeters, 2.13 centimeters, 1.5 centimeters, and 2.9 centimeters. In this, the formula for apparent depth is given as apparent depth equals real depth upon the refractive index. Now the refractive index of the liquid is given as 1.63. So therefore the apparent depth would be the real depth, that is 12.5 centimeters upon 1.63. So the needle would be in focus at an apparent depth of 7.67 centimeters. Now initially the needle was in focus at a distance of 9.4 centimeters. So therefore the distance that the microscope have to be shifted would be equal to 9.4 minus 7.67. So which comes out to be 1.73 centimeters. Hence option A is the correct answer. A vessel of depth x is half filled with oil of refractive index mu1 and the other half is filled with water of refractive index mu2. The apparent depth of the vessel when viewed from above is, the options given are x mu times mu1, x mu1 plus mu2 upon 2 times mu1 mu2, x into mu1 mu2 upon 2 times mu1 plus mu2, x into mu1 mu2 upon mu1 plus mu2, and the last option is 2x into mu1 plus mu2 upon mu1 mu2. Now let's assume this as the vessel of height x. So the half distance or half depth, that is x by 2, is filled with water and the other half is filled with oil. So the total depth or the total height of x can be found out as apparent height or apparent depth is nothing but real height or real depth upon the refractive index. So now since there are two liquids, so the overall apparent depth would be equal to real height for the first liquid, that is x by 2, divided by the refractive index of the first liquid, that is mu1, plus real height for the second liquid, oil, into mu2. So let's take x by 2 common. You get 1 upon mu1 plus 1 upon mu2. So simplifying this, we get x times mu1 mu2 upon 2 times, x times mu1 plus mu2, 2 times mu1 mu2. Hence option A is the correct answer. A tank is filled with water to a height of 15.5 cm. The apparent depth of a needle lying at the bottom of the tank is measured by a microscope to be 8.5 cm. If the water is replaced by a liquid of refractive index 1.94 up to the same height, by what distance would the microscope have to be moved to focus on the needle again? Options given are 1 cm, 2.37 cm, 0.52 cm, and 3.93 cm. This is similar to the previous problem one that we've done. The apparent depth equals to the real depth upon the refractive index mu. Now the real depth is the height up to which the water is filled or the liquid is filled in the second case is 15.5. So 15.5 divided by the refractive index of the second liquid that we want to find out, that is 1.94. So this comes out to be 7.98. So 7.98 centimeters is the apparent depth with the new liquid. So now we have to move the microscope from 8.5 to 7.98. So 8.5 minus 7.98 gives you 0.52 centimeters. Hence option C is the correct answer. A ray of light traveling in a transparent medium of refractive index mu falls on a surface separating the medium from air at an angle of incidence 45 degree. For which of the following value of the mu the ray can undergo total internal reflection? The options given are 1.33, 1.40, 1.50 and 1.25. Now for a ray that is coming from a medium, denser medium to a rarer medium, it is air. So the total internal reflection would occur when the angle of incidence I is greater than the critical angle. So I when greater than the critical angle C. So sin I when greater than sin C, the total internal reflection takes place. So for limiting case, let's consider sin I equals sin C. But sin C is given by 1 by refractive index. So sin I is equals to 1 upon mu. Therefore mu is equals to 1 upon sin I. So 1 upon sine of I is given as 45 degrees. So sine of 45 is 1 by root 2. Therefore mu is equals to 1 upon 1 by root 2. So which can be written as root 2. And the value of root 2 is 1.414. So approximately option B is the correct answer. Light travels in two media A and B with speeds 1.8 into 10 raised to 8 meters per second and 2.4 into 10 raised to 8 meter per second respectively. Then the critical angle between them is, the options given are sine inverse of 2 by 3, tan inverse of 3 by 4, tan inverse of 2 by 3 and sine inverse of 3 by 4. Now here velocity in medium A is given as 1.8 into 10 raised to 8 meters per second and velocity in medium B is given as 2.4 into 10 raised to 8 meters per second. Now as we know that light travels slower in denser medium, so the medium A is denser as compared to medium B. Now we also know that sin C or the critical angle is given by 1 upon the refractive index of the denser medium with respect to the rarer medium. So this can be written as mu of the rarer medium with respect to the denser medium. So in order to find out mu of B with respect to A, we can divide the velocities. So velocity in A upon velocity in B. So that is equals to 1.8 into 10 raised to 8 upon 2.4 into 10 raised to 8. So this comes out as 3 by 4. So mu of A B with respect to A is 3 by 4. So therefore C is equals to sine inverse of 3 by 4. Hence option D is the correct answer. A screen is placed 90 centimeters away from an object. The image of the object on the screen is formed by a convex lens at two different locations separated by 20 centimeters. Find the focal length of the lens. The options given are 42.8 centimeters, 21.4 centimeters, 10.7 centimeters and 5.5 centimeters. Now a screen and an object are placed 90 centimeters apart. So let us consider two cases. The first in which the lens is placed at a distance of u1 from the object and v1 from the screen. So therefore u1 plus v1 is equals to 90. Now a second case in which the same object is placed but the lens the distance of the lens from the object and the screen are interchanged. So the object comes at a distance of v1 and the screen is at a distance of u1. So, and this is done by moving the lens through a distance of 20 centimeters. So after moving 20 centimeters, u1 and v1 are interchanged. So basically from this we can we can come to that v1 minus u1 is equals to 20. So solving these equations 1 and 2, we get the values of u1 and v1 as u1 equals 35 centimeters and v1 equals 55 centimeters. Now applying the general lens formula, that is 1 upon v minus 1 upon u is equals to 1 upon the f of focal length. So as we know, in the lens formula all the distances are measured with respect to the lens. So towards the right, the screen v1 is given as 1 upon 55 plus, since the object is placed towards the left, so it will come as 1 upon u, that is 35, but since it is towards the left we will take it as minus 35, is equals to 1 upon the focal length of the lens. So 1 upon 55 plus 1 upon 35 equals 1 upon f. This minus and minus together turn into a plus. Therefore the focal length f is equals to 55 into 35 upon 55 plus 35. So after solving this we get the answers 21.4 centimeters, hence option B is the correct answer. A convex refracting surface of radius of curvature 20 centimeters separates two media of refractive indices 4 by 3 and 1.6. An object is placed in the first medium of mu 4 by 3 at a distance of 200 centimeters from the refractive surface. The position of the image formed is, the options given are 120 centimeters, 240 centimeters, 100 centimeters and 160 centimeters. So let us consider this as a space. So there is a refracting surface or concave surface, a convex surface. So this is medium A of mu equals 4 by 3 and this is a medium B of refractive index equals 1.6. So an object is placed over here. Object is placed over here at a distance of 200 centimeters and the rays of this would converge to form the object over here, an image of the object over here. So we need to find out this distance. So basically, since there are two different media involved, the lens formula, the general lens formula, which is given as 1 by v minus 1 by u equals 1 by f, this gets slightly modified as mu2 upon v minus mu1 upon u is equals to mu2 minus mu1 upon the f or the radius of curvature r. So therefore the image object distance is 200 and since it is to the left, we will write mu2 is 1.6 upon v, that is the distance we need to find out, minus mu1 is given as 4 by 3 and since the object is placed at a distance of 200 towards the left, so this minus would become into a plus, is equals to mu2 minus mu1. So 1.6 minus 4 by 3 upon r. R is given as 20 centimeters. So therefore solving this we will get the value of v as 240 meters. Hence option B is the correct answer. A biconvex lens has a focal length 2 by 3 times the radius of curvature of either surface. The refractive index of the lens material is, the options given are 1.75, 1.33, 1.5 and 1.0. Now for a biconvex lens, the radius of curvature of this surface, since it is, let's consider R1 and R2. Since this is on the left, so R2 would be taken as negative, whereas the radius of curvature of this point, which is on the right, will be taken as positive. So the formula for focal length is given as 1 by f equals mu minus 1, that is the refractive index, minus 1 upon R1 minus 1 upon R2. But since R2 is on the left side, R2 would be negative, so the negative of negative will turn out to be positive. So therefore, the value of f is given as 2 by 3 times R. So you can write it as 3 upon 2 R is equals to mu minus 1 upon R plus 1 upon R. So therefore the R in this 3 upon 2 R is equals to mu minus 1. This comes out, this would become 2 upon R. So R gets cancelled. Therefore 3 by 4 is equals to mu minus 1. Therefore mu equals 3 by 4 plus 1. So that is nothing but 7 by 4. And 7 by 4 is nothing but 1.75. Hence option A is the correct answer. A convex lens of focal length 0.2 meters and made of glass, the refractive index of glass with respect to air is given as 1.5, is immersed in water of refractive index of water with respect to air is 1.33. Find the change in focal length of the lens. The options given are 5.8 meters, 0.58 centimeters, 0.58 meters and 5.8 centimeters. Now the focal length 1 upon f is given as mu. Now let's consider the glass with respect to air. So mu of G with respect to air minus 1 upon R1 minus 1 upon R2. So from this formula, let us find out the value of 1 upon R1 minus 1 upon R2. Therefore the focal length is given as air as 0.2 is equals to 1.5 minus 1 times 1 upon R1 minus 1 upon R2. So 1 upon 0.2 equals 1 upon 5 minus 1 is 0.5 from 1 upon R1 minus 1 upon R2. So therefore 1 upon R1 minus 1 upon R2 is equals to 0.5 into 0.2, and the reciprocal, it comes out to be 10. Now let us consider the focal length in water. So this was the focal length in air. Now the focal length in water would be given by mu of glass with respect to water minus 1 into 1 upon R1 minus 1 upon R2. However, the value of mu of glass with respect to water is not given. So therefore, mu of glass with respect to water can be given as mu of glass with respect to air upon mu of glass mu of water with respect to air. So this is 1.5 upon 1.33. So the value comes out as 1.128. Now substituting this value of mu of glass with respect to water in this formula, we get 1 by Fw. So 1 by Fw is equals to 1.128 minus 1 times 1 by R1 minus 1 by R2 is 10. So this is Fw is equals to 1 upon 1.28. Okay, so that is equals to 0.7 8. Now 0.78 is the focal length in water. So the change would be 0.2 or 0.78 minus 0.2, which is equals to 0.58. Now since all the units are in meters, since we haven't changed any unit, therefore option C, 0.58 meters, is the correct answer. A real image of an object is formed at a distance of 20 centimeters from a lens. On putting another lens in contact with it, the image is shifted 10 centimeters towards the combination. The power of the lens is, the options given are 2D, 5D, 6D and 10D. Now since the image formed is real, therefore the lens should be convex and the image is formed at a distance of 20 centimeters. So the image distance V is 20 centimeters. Let us consider f1 is the focal length for this first lens. Now for the first lens, applying the lens formula, 1 upon f1 is equals to 1 upon v, that is 20 minus 1 upon u. Now when this first lens is combined with another lens of focal length f2, so f1 and f2 together they shift the image 10 centimeters towards the combination. So this is f1 and say this is f2. So the image which was over here is now shifted over here, so 10 centimeters towards the combination. Hence the image distance V becomes now 20 minus 10 centimeters, so that is equals to 10 centimeters. So applying again the general lens formula, 1 upon V now becomes 10 minus 1 upon U is equals to 1 upon F1 plus 1 upon F2. Now instead of F1 we can write 1 upon 20 minus 1 upon U. So 1 upon 10 minus 1 upon U is equals to 1 by 20 minus 1 by U plus 1 by F2. So this gets cancelled. So we are left with 1 by F2 is equals to 1 by 10 minus 1 by 20. So F2 turns out to be 20 centimeters. So the power of the lens is given by 1 upon the focal length, but in meters. So since this is centimeters, to convert it into meters, 100 upon 20. So that is nothing but 5. So 5D. Hence option B is the correct answer. Double convex lenses are to be manufactured from a glass of refractive index 1.55 with both faces of same radius of curvature. What is the radius of curvature required if the focal length is to be 20 centimeters? The options given are 11 centimeters, 22 centimeters, 7 centimeters and 6 centimeters. Now, in order to solve this sum, let's use the lens maker's formula, that is 1 upon f or 1 upon focal length is equals to mu minus 1 upon r1 minus 1 upon r2. Now since it's given that both the surfaces have the same radius of curvature, so r1 and r2 can be assumed to be a value r. Now r1 is the object distance and whereas r2 is the image distance. Now so one of them has to be negative, so 1 upon, so r2 is nothing but minus r. Therefore the formula changes as 1 upon f is equals to mu minus 1 upon r1, and instead of r1 we write r minus 1 upon minus r. So this minus minus becomes plus as mu times mu minus 1 upon r plus 1 upon r. So 1 by f, the focal length is required to be 20 centimeters. So that is written as 20. So 1 upon 20 is equals to, the refractive index is given as 1.55. minus 1, 1 upon r plus 1 upon r can be written as 2 upon r. So solving this to get the value of r as 22 centimeters. Hence option B is the correct answer. A thin glass sheet of refractive index 1.5 lens has power of minus 8D in air. Its optical power in a liquid medium of refractive index 1.6 will be, the options given are 1D, minus 1D, 25D and minus 25D. Now, in air, using the lens maker's formula, power is nothing but 1 upon focal length in meters. So, according to lens maker's formula, 1 upon f can be given as mu of glass with respect to air minus 1 upon r1 minus 1 upon r2. Similarly, power in the medium or liquid of refractive index 1.6 can be given as mu of glass, but with respect to the medium now, or the liquid, minus 1 upon r1 minus 1 upon r2 again. So the value of mu of glass with respect to air, with respect to liquid, can be given as mu of glass with respect to air upon mu of glass, mu of liquid with respect to air. So therefore, you can write P dash, or the power in the medium upon power in the air, as mu of G upon mu of L minus 1 into 1 upon R1 minus 1 upon R2, the whole thing divided by that in the air as mu of G minus 1 upon R1 minus 1 upon R2. So these gets cancelled. So this can be written as 1.5 upon 1.6 minus 1 upon 1.5 minus 1. So this is nothing but 1.5 minus 1.6 is minus 0.1 upon 1.6 upon 1.5 minus 1 is 0.5. So P dash is equals to has a value of minus 8. So this can be written as 1 minus of 1 into 2 upon 16 into 1 times P. So that is minus 1 by 8 times minus 8D. So minus 8 minus 8 and the minus minus gets cancelled out as 1D. Hence option A is the correct answer. Light from a point source in air falls on a spherical glass surface whose radius of curvature and refractive index are 20 centimeters and 1.5 respectively. If the distance of light source from the glass surface is 100 centimeters, then at which position image will be formed? The options given are 25 centimeters, 50 centimeters, 100 centimeters and 200 centimeters. So basically there's a glass and there's an object over here. So due to the curvature of the glass, the object is formed inside the glass. Hence there are two mediums involved. Medium 1 mu1 which is air and medium 2 which is glass. So the modified lens formula can be written as mu2 upon V minus mu1 upon U is equals to mu2 minus mu1 upon f, or the refractive the radius of curvature r. Now since U is towards the left of the glass or towards the left of the lens in this case, so U is taken as negative. So therefore U will be minus 100. So So therefore mu2 is given as 1.5. So 1.5 upon v minus mu1, that is air, but u is minus 100, so minus 100 is equals to mu2 1.5 minus 1 upon the radius of curvature is 20 centimeters. So therefore 1.5 v 1.5 upon v plus 1 by 100 is equals to 0.5 upon 20. So 1.5 upon v is equals to 0.5 upon 20 can be written as 1 by 40, and this goes as minus 100. So let's write this as 3 upon 2v multiplying and dividing by 2 is equals to, this can be written as the like RHS can be written as 3 upon 200. It can be simplified as 3 upon 200. Therefore the value of v comes out as 100. Hence the object or the image is formed at a distance of 100 centimeters. Hence option C is the correct answer. What is the refractive index of a material of plane convex lens if the radius of curvature of the convex surface is 10 centimeters and the focal length of the lens is 30 centimeters? The options given are 6 by 5, 7 by 4, 2 by 3 and 4 by 3. Now for a plane convex lens, uh, the value of R1 would be infinity, since the side is plane, therefore it would have an infinite radius of curvature, whereas R2 is given as 10 centimeters. Now, and focal length f is given as 30 centimeters. So applying the lens maker's formula, 1 by f is equals to mu minus 1 by r1 minus 1 by r2. The value of r2, since it is on the left side, can be taken as negative. Therefore 1 by 30 is equals to mu minus 1 by r1, which is infinity, minus 1 upon minus 10. So therefore 1 by 30 is equals to mu minus 1 times 1 by infinity can be considered as 0, and minus minus becomes plus as 1 by 10. So therefore this and this gets cancelled, and 1 by 3 is equals to mu minus 1. So therefore mu is equals to 1 by 3 plus 1, that is equal to 4 by 3. Hence option D is the correct answer. The radii of curvature of surfaces of a double convex lens are 20 centimeters and 40 centimeters respectively, and its focal length is 20 centimeters. What is the refractive index of the material of the lens? The options given are 5 by 2, 4 by 3, 5 by 3 and 4 by 5. Now using the lens maker's formula, 1 by f is equals to mu minus 1 times 1 upon r1 minus 1 upon r2. The value of r1 is 20 centimeters given, and the value of r2 is 40 centimeters. However, since it's a double convex lens, r1 and r2, the r1 is on the right, however the r2 is on the left, hence r2 would become negative. So therefore 1 by 20, that is the focal length, is equals to mu minus 1 times 1 upon r1, which is 20, minus 1 upon minus 40. Therefore 1 by 20 is equals to mu minus 1. This can be simplified as 3 upon 40, and therefore mu minus 1 is equals to, this taken on this side comes out as 2 by 3, and therefore mu is equals to 2 by 3 plus 1. Now mu is equals to 5 by 3. Hence option C is the correct answer. A converging lens is used to form an image on the screen when the upper half of the lens is covered by an opaque screen. The options given are half the image will disappear, complete image will disappear, intensity of the image will decrease, intensity of the image will increase. So let's assume this is an object over here, and this is a converging screen, converging lens, and this is a screen. Now the rays of light from this from the object converge at this point to form the image. However, now suppose if the top half of the screen has been blocked. So since the light doesn't pass through this half, so therefore only half of the light is going. However, the image, complete information about the image passes through each and every ray. Hence, the image won't be half, but however, the intensity, since not more number of light rays are passing through, so the intensity would decrease. However, the image would be complete. Hence, option C is the correct answer. A mark placed on the surface of a sphere is viewed through glass from a position directly opposite. If the diameter of the sphere is 10 cm and refractive index of glass is 1.5, the position of the image will be, the options given are minus 20 cm, 30 cm, 40 cm and minus 10 cm. Now, let us assume this is a spherical glass. On this, at this point, there is a mark, and the viewer is over here. Now this mark is due to this, is refracted by this radius or this curve of the lens, and due to this we find a apparent distance in this of this mark. So using the lens formula or the modified lens formula, since there are two mediums involved, mu2 and mu1. Mu1 is the air and mu2 is the glass itself. So therefore mu2 upon minus u, mu2 upon minus u plus mu1 upon u upon v is equals to mu1 minus mu2 upon r. Now mu1 is air, and so that is the value is 1, mu2 is 1.5 for glass. The value of u will be the diameter, equal to the diameter of the spherical glass, so that is 10 centimeters. However, since it is on the left, we'll write it as minus 10 plus the value of v, so the minus of minus 10 becomes plus later on, and the value of v is what we want to find out. And mu1 minus mu2 is 1.5 minus 1 upon the radius of curvature would be 5. So therefore this turns out to be 1.5 upon 10 plus 1.1 by v is equals to 1 by 10, and therefore 1 by v is equals to 1 by 10 minus 3 by 20. This 1.5 upon 10 is multiplied by 2 into 3 by 20. So 1 by v is equals to minus 1 by 20, and therefore the value of v comes out as minus 20 centimeters. Hence option A is the correct answer. An object is placed at a distance of 1.5 meter from a screen and a convex lens is interposed between them. The magnification produced is 4. The focal length of the lens is, the options given are 1 meter, 0.5 meters, 0.24 meters and 2 meters. Over here, this is a screen, this is the object. Let's say a lens has been placed between them. So the object distance is u and the image distance, let it be v. So magnification is given as 4, which can be which is the ratio of the image distance to the object distance. So therefore u is equals to v upon 4. But however, since u is on the left of the lens, u can be considered as minus v by 4. Also u plus v is equals to 1.5 meters. Therefore, let's write u as v by 4 plus, let us just consider the magnitudes and not the direction over here. So v by 4 plus v is equals to 1.5. Therefore from this the value of v, we get it as 1.2 meters, and hence the value of u comes as 1.2 upon 4, which is 0.3 meters. But however, 0.3 meters towards the left, so u is minus 0.3 meters from the lens. Now the using the lens formula, 1 upon f is equals to 1 upon v minus 1 upon u. Therefore f is equals to v into u upon u minus v. So v into u, that is minus 1.2 into minus 0.3 upon minus 0.3 minus 1.2. On solving this, we get 0.24 meters. Hence, option C is the correct answer. The image of the needle placed 45 centimeters from a lens is formed on a screen placed 90 centimeters on the other side of the lens. The displacement of the image if the needle is moved by 5 centimeters away from the lens is, the options given are 10 centimeters towards the lens, 15 centimeters away from the lens, 15 centimeters towards the lens, and 10 centimeters away from the lens. Let us consider a lens. This is a screen on which the image is formed, and this is the object initially. Now initially it is 45 centimeters and this is 90 centimeters. Now using these values, let us find out the focal length of the lens. So 1 by f is equals to 1 by 90 minus 1 by minus 45, since it is on the left. So that turns out to be 1 by 30. So the focal length of the lens is 30 centimeters. Now since the needle is moved 5 centimeters away, so it is further moved 5 centimeters. So the new distance of u is equal to 50 centimeters. And therefore we need to find out the distance by which the screen must be moved in order to get a focused image. So that will be the new value of v dash. So again applying the lens formula, 1 by f is equals to 1 by v minus 1 by u. Therefore 1 by v is equals to 1 by f plus 1 by u. So 1 by f is 30 plus 1 by u is now minus 50. So 1 by 30 minus 1 by 50. So this comes out to be 2 by 150. So v dash is equals to 75 centimeters. So the new screen has to be placed at a distance of 75 centimeters. And since 75 is less than 90, so basically we need to move the screen towards the lens. So 75 centimeters should be the new distance, and so the displacement should be done of 90 minus 75, that is equal to 15 centimeters towards the lens. So 15 centimeters towards the lens, option C is the correct answer. The angle of minimum deviation for prism angle pi by 3 is pi by 6. If the velocity of light in vacuum is 3 into 10 raised to 8 meters per second, then the velocity of light in the material of the prism is, the options given are 2.12 into 10 raised to 8 meters per second, 1.12 into 10 raised to 8 meters per second, 4.12 into 10 raised to 8 meters per second, and 5.12 into 10 raised to 8 meters per second. Now using the formula, refractive index for a prism is given as sine of A plus delta m upon 2, the whole thing divided by sine of A by 2. The A over here is nothing but the prism angle given as pi by 3, and delta m is the minimum deviation angle, that is pi by 6. So therefore mu is equals to sine of pi by 3 plus pi by 6. Pi by 3 can be written as 60 degree and pi by 6 is 30 degree. So 60 plus 30 upon 2 into sine of 60 by 2. So now sine 60, first of all sine 60 plus sine 30, sine of 60 plus 30, that is sine 90. So sine 90 by 2. So sine 90 by 2 is sine 45, and sine 60 by 2 it will be sine 30. So sine 45 is 1 by root 2, which can be written as 0.7071 upon sine of 30 is half, that is can be written as 0.5. So the value of mu comes out as 1.414. Now since they are given the value or the velocity of velocity of light in vacuum, v is given as uh, c is given as 3 into 10 raised to 8. Therefore mu can be written as c upon v, velocity of light in the medium. So velocity of light in the medium v can be found out of c upon mu, that is 3 into 10 raised to 8 upon mu is 1.414. Therefore velocity of light in the medium is 2.12 into 10 raised to 8 meters per second. Hence option A is the correct answer. For a glass prism, mu is equal to root 3. The angle of minimum deviation is equal to the angle of prism. The angle of prism is, options given are 45 degrees, 30 degrees, 90 degrees and 60 degrees. So using the prism formula, mu is equals to sine of A plus delta m upon 2 upon sine of A by 2. Now in this case A is equals to delta m, the angle of prism equals to the minimum angle of deviation. So therefore mu can be rewritten as sine of A plus A, that will be 2A upon 2 upon sine of A by 2. So this 2 gets cancelled, so sine A upon sine of A by 2. So let's simplify this. Mu is equal to sine A can be written as 2 times sine of A by 2 cos A by 2 upon sine A by 2. So these gets cancelled. So mu is equal to 2 times cos of A by 2. Mu is given as root 3. So root 3 upon 2 is equals to cos of A by 2. Therefore A by 2 is equals to cos inverse of root 3 upon 2. So cos inverse of root 3 upon 2, A by 2 is equals to cos inverse of root 3 upon 2 is nothing but 30 degrees. Therefore A will be equal to 30 into 2, that is 60 degrees. Hence option D is the correct answer. A ray is incident at an angle of incidence I on one surface of the prism of small angle A and emerges normally from the opposite surface. If the refractive index of the material of prism is mu, the angle of incidence I is nearly equal to, options given are A by mu, A by 2 mu, mu times A and mu A upon 2. Let's draw a prism. This is the central angle of prism A. Supposing this is the angle of incidence I, the ray gets diffracted and then again it gets refracted. However, in this case it comes out as a normal to the second surface, comes out normal from the opposite surface, and therefore this angle R1 is the angle of incidence and R2 that would be the angle with which so R2 would be 0 since it is normally coming out from the second surface, and as we know A is equals to R1 plus R2, but however since R2 is equals to 0, therefore A is equals to R1. Now according to Snell's law, mu is equals to sine I upon sine R1. So therefore mu is equals to sine I upon sine of A, since R1 and now A is equals to R1. Since it is a small prism, since the angle is small, therefore sine I is approximately equal to I and sine A is approximately equal to A. Therefore the value of I is approximately equal to mu times A. Hence option C is the correct answer. Which of the following colors of white light deviate the most when passed through a prism? The options given are red light, violet light, yellow light, both A and B. That is red and violet light. Let's see a prism. When a white light is incident on this, so it comes out in the form of 7 different colors of the rainbow. So that is V, I, B, G, Y, O and R in the form of a Vibgyor. That those are the colors of the rainbow. As we can see, since the speed of violet component of the light is slower as compared to red, so violet light or the violet part of the spectrum is deviated much more as compared to the red. Hence, option B, violet light, it deviates the maximum, is the correct answer. Which of the following statement is correct? At sunrise or sunset, the sun's rays have to pass through a small distance in the atmosphere. The option B is at sunset or sunrise, the sun's rays have to pass through a larger distance in the atmosphere. Rayleigh scattering is proportional to 1 by lambda square. And the fourth option is most of the blue and other short wavelengths are not removed by scattering. Let us look at each of the options. For option A, this is the planet Earth, and at sunrise or sunset, the sun is at the equator, the sun is at the horizon, and hence it has to travel through a longer distance to reach the eye, and hence option A is incorrect. Option B, at sunrise or sunset, the sun's rays have to pass through a larger distance in the atmosphere. Just as explained, since it is at the horizon, the sun's rays have to pass through a longer distance. So option B is correct. However, let's look at the option C. Rayleigh scattering is proportional to 1 by lambda square. Incorrect, because Rayleigh scattering is proportional to 1 by lambda fourth power, and most of blue and the other shorter wavelengths are not removed by scattering. This is also incorrect. The shorter wavelengths such as blue, violet, all these are scattered to a larger extent, and hence option D is also incorrect. Hence option B is the correct answer. The focal length of the lenses of an astronomical telescope are 50 centimeters and 5 centimeters. The length of the telescope when the image is formed at the least distance of distinct vision is, the options given are 45 centimeters, 55 centimeters, 275 by 6 centimeters, 325 by 6 centimeters. Now here, uh, the focal lengths of the telescope, object object focal length is 50 centimeters and the eyepiece focal length is 5 centimeters, and the distance of distinct vision, least distinct of distinct vision, is 25 centimeters. That's a known fact. So the length of the telescope can be given by the formula L is equals to F naught or F0 plus Fe times D upon Fe plus D. So substituting these values, we get 50 plus 5 into 25 upon 5 plus 25. So solving this much part, we get 50 plus 25 upon 6. So the length of the telescope comes out to be 325 upon 6 centimeters. Hence option D is the correct answer. A giant telescope in an observatory has an objective of focal length 19 meters and eyepiece of focal length 1 centimeter. In normal adjustment, the telescope is used to view the moon. What is the diameter of the image of the moon? Dia of the moon is given as 3.5 into 10 raised to 6 meters, and the radius of the lunar orbit around the earth is 3.8 into 10 raised to 8 meters. Now in this case, since the image or the object distance u is much greater than the objective focal length, u, that is the distance of the moon from the telescope, and f is the focal length of the objective lens. Now since u is much greater than the focal length objective, it is safe to assume that the image distance is at the focal length of the objective lens, that is nothing but 19 meters. Now the magnification m is given by the ratio of image distance to the object distance. So that can be 19 upon 3.8 into 10 raised to 8 meters. This is the distance of the moon from the telescope, and hence this will be our object distance. So this comes out to be 0.5 into 10 raised to minus 7. Now the diameter that would be viewed, diameter of the image would be the actual diameter into 10 raised to 6 multiplied by the magnification. So 0.5 into 10 raised to minus 7. So this comes out as 0.175 meters, or it can be said as 17.5 centimeters. Hence, this is the answer, 17.5 centimeters. A small telescope has an objective lens of focal length 144 centimeter and an eyepiece of focal length 6 centimeter. What is the separation between the objective and the eyepiece? The options given are 0.75 meter, 1.38 meters, 1 meter and 1.5 meter. Now the objective lens focal length is given as 144 centimeter, which can be written as 1.44 meters, whereas the eyepiece focal length is given as 6 centimeter, which can be written as 0.06 meters. Now the separation between the objective and the focal objective and the eyepiece lens uh, is nothing but the length of the telescope tube. So which is objective focal length plus eyepiece focal length. That is 1.44 plus 0.06. So it is 1.50 meters. Hence this is the separation between them. Hence option D is the correct answer. In a compound microscope, the focal lengths of two lenses are 1.5 cm and 6.25 cm. If an object is placed at 2 cm from the objective and final image is formed at 25 cm from the eye lens, the distance between the two lenses is options given are 6 cm, 7.75 cm, 9.25 cm and 11 cm. Now in this, the objective focal length is given as 1.5 centimeters. The eyepiece focal length is given as 6.25 centimeters. The object distance from the objective length is minus 2 centimeters, since it is placed at 2 centimeters, and the final image formed from the eyepiece at a distance of 25 centimeters. However, it will come with a minus sign by referring to this figure. This is a compound microscope. This is the objective lens and eyepiece. Now the object is placed towards the left of the objective lens, hence a negative and 2 centimeters. This forms a virtual image over here. This forms a real image over here, and this real image serves as the source for the eyepiece, and due to which a second virtual image is formed at a distance of VE. So the final VE is at a distance of 25 centimeter. However, since it is to the left, we take it as negative. Now, so in order to solve this sum, let us consider first the objective lens. So for objective lens, using the lens formula, 1 upon f0 is equals to 1 upon v0 vo upon 1 upon minus 1 upon uo. So uo is minus 2 centimeters, and therefore from this we can find out 1 upon vo is equals to 1 upon 1.5 minus 1 upon 2. So VO is equals to 6 centimeters. So this is nothing but 6 centimeters. Now for this eyepiece, for eyepiece, again applying the lens formula, 1 upon Fe is equals to 1 upon Ve minus 1 upon Ue. Now as we can see, the VO at the distance VO serves as UE. Okay, so and the final VE is given at a distance of 25 centimeters. Therefore, 1 upon 6.25 is equals to 1 upon VE is given as 25, but since on the left we take it as minus 25, minus 1 upon UE. Therefore, to solve this, we get minus 1 upon UE is equals to 1 upon 6.25 plus 1 upon 25. Therefore, UE, we get it as minus 5 centimeters. So therefore, this UE is at a distance of minus 5 centimeters. So therefore, the total distance between the two lenses is the magnitude of V naught or VO plus magnitude of UE. So that is equals to 6 centimeters plus 5 centimeter, that is 11 centimeters, and hence option D is the correct answer. A microscope is focused on a mark on a piece of paper and a slab of glass of thickness 3 cm of refractive index 1.5 is placed over the mark. How should the microscope be moved to get the mark in focus again? The options given are 4.5 cm downwards, 1 cm downward, 2 cm downward and 1 cm upward. Now suppose this is a paper on which a glass slab is placed. Initially, the real depth of the mark is 3 centimeters. However, due to the glass, it will appear to be having an apparent depth. So, if initially the microscope was over here, it needs to be moved in the upward direction so that it can focus at this point. So basically the microscope has to be moved upwards. And so in order to find out the actual value, so let this distance be O and let this point be O dash. So in order to focus, the microscope has to be moved through a distance of O dash. So that is nothing but real depth of the mark minus the apparent depth. So real depth of the mark minus the apparent depth is O dash, and that's what the distance should be moved by the microscope. So real depth is 3 centimeters, whereas the apparent depth can be given as real depth upon the refractive index 1.5. So 3 minus 2, that is equal to 1 centimeter. Therefore, the microscope has to be moved 1 centimeter upward. Option D is the correct answer. Light incident normally on a plane mirror attached to a galvanometer coil reflects backward as shown in the figure. A current in the coil produces a deflection of 3.5 degree of the mirror. The displacement of the reflected spot of light on a screen placed 2 meters away is. The options given are 27.5 meters, 48.9 centimeter, 24.5 centimeter and 12.2 meters. So in this is the mirror when in the normal position, and this is the mirror when the deflection has occurred due to the current flowing through the galvanometer. Now what we need to know here is that angle of deflection of the mirror is 3.5 degrees. However, since the mirror is deflected 3.5 degrees, the reflected ray would reflect at an angle of 2 theta, that is 2 times this. So reflected ray angle 2 theta is equal to 7 degrees, and the distance between the screen and this mirror is given as 2 meters. So therefore tan of 2 theta is equals to d, that is opposite upon 2. So therefore d is equals to 2 into tan of 2 theta. This 2 times tan of 7 degree. Now tan 7 degree is 0.1227. So that is equal to 0.245 meters. So that is 24.5 centimeters. Hence option C is the correct answer.